So now we go to a brand new set of topics. These are basically gonna go through concepts in calculus. For some, this may be a review, but for others that's encountering this for the first time, we'll go through the concepts slowly, especially concepts in differentiation that is pertinent to economics. The first thing we'll learn is the concept of a limit. Okay, so suppose we have a function f that takes as input a variable x. So the function f takes input x and spits out whatever. Okay, it's a mapping from x to another element. Okay, so if the value f of x approaches L, okay, if a certain value, if the value of the function f of x approaches L, as x approaches a certain value a, we say that the limit of f of x as x approaches a is L. Okay, so as you go closer and closer and closer to a, the value of the function gets closer and closer to L. Then we say that the limit of the function f of x is L when x approaches a. So in notation, you have this. This is the limit notation. So you read this as the limit of f of x as x approaches a. The arrow says that x will approach a is equal to L. Okay, so as x approaches a, if x gets closer and closer to a, then the value of the function gets closer and closer to L. So that's a limit. So if x is a real number, you can locate it at the real number line. There are basically two ways by which you want to approach a. Okay, you can either approach a from values that are less than a. So from example here, going closer and closer to a. So you approach a from the left. Okay. The other way of approaching a is for values bigger than a. So you start somewhere here, then go closer and closer to a, and therefore you approach a from the right. You start with values larger than a, and then you go closer and closer to a. Now, if you approach a from the left, and you see that the value of the function f of x is approaching a certain number L of L, okay, that L of L is called the left hand limit. Okay, so if x, the variable x, approaches a from the left, this negative sign here or this minus sign here indicates that you're approaching a from the left. Okay, now as you approach a from the left from values smaller than a, and then the value of the function approaches a number L of L, then that L of L is called the left-hand limit of the function. Okay. On the other hand, if you approach a from values bigger than a, or in other words, from the right, so this is the notation. So you approach x, you let x approach a from the right. This positive here, this positive symbol over here says you're approaching a from the right. And if you approach a from the right and that value of the function approaches a number L of R, okay, L sub R, then that L sub R is called the right hand limit. Okay, so it's not necessarily this, these limits are not necessarily the same, as we shall see later. Okay, so if you're approaching a from the left, and that limit is called the left-hand limit. If you're approaching a from the right, then this limit is called the right-hand limit. So here's an example. You have this function f of x over here. Now this f of x has two domains. So first, this domain from -1 to 0. Okay, so it's basically this side. Notice that 0. This is not this is a strict inequality. Okay, so 0 is not included there. So this is the graph of this function x plus 1. Okay, so if x is -1, then your f of x is equal to 0. That's this point. Okay, and then to the right of 0, so from 0 to 1, this is the relevant function, x minus 1. So if x equals to 0, for example, then your f of x equals to -1. This is this point. As you go to 1, if x equals to 1, your f of x, if x equals to 1, your f of x would be 1 minus 1 equals to 0. That's this point. So this graph over here corresponds to this segment of the function. This graph over here corresponds to this segment of the function. Okay, now notice that if you uh, if you approach, say, 0 from the left, okay, so what does that mean? You approach, x approaches 0 from the left, so you start with values bigger than 0, say -1 first. Then if x equals to -1, then f of x is equal to 0. Okay, now you approach, you go closer and closer to 0. So for example, you have 0.5, -0.5 over here. So your y, your f of x is, if x equals to -0.5, then your f of x is equal to -0.5 plus 1, it's 0.5. Okay. Okay. Now let's do closer. Now it's negative 0.25. Okay. So if x is -0.25, then f of x would be -0.25 plus 1 is positive 0.75. Okay, so go closer and closer. What do you notice? This value of the function, which started from 0, then became 0.5, then became 0.75. As you go closer and closer to 0, this part of the function over here approaches 1. Okay, but it's not defined at 0. Okay, so it just approaches 1. So if you approach x, if you approach 0 from the left, okay, as x approaches 0 from the left, then the limit of this function approaches 1. Okay, so the left hand limit here in this case approaches 1 as you approach, as x approaches 0 from the left. Okay, great. Now let's approach 0 from the right, meaning from values bigger than 0. If you have x equals to 1, then you have f of x. This is now the relevant part of the function. So f of x is equal to 0. Okay, that's this um, that's this point here. Then if x equals to 0.5, then f of x is equal to 0.5 minus 1, then it's equal to negative 0.5. Okay, this is if x is if x is 0.5, then this is negative 0.5. Okay, now let's look at something closer to 0. Say x equals to 0.25. F of x in this case would be negative 0.75. Okay, via this part of the function. So what do you notice? As x approaches 0 from the right, okay, you're beginning with values bigger than 0, and you approach 0 from the right, then you notice that f of x here will go closer and closer and closer to -1. Okay, so as x approaches 0 from the right, okay, the value of f of x approaches -1. So we write it this way. As you approach x, as x approaches 0 from the right, then the value of the function approaches -1. Okay, so this is the right hand limit. Okay, this is the right hand limit, and this is the left hand limit. Okay, now what do you notice? In this case, the left hand limit and the right hand limit are not the same. Okay, so it's not necessarily true that the left hand limit and the right hand limits are the same. Okay, there are instances when they are different. Now, in the instance when the left hand limit is equal to the right hand limit, then we refer to that common value as just the limit. Okay, again, when your left hand limit is the same as your right hand limit, then that common value is called the limit. So here's the formal definition. If x is a function of a variable x, of one variable x, then x, the limit of f of x as x approaches a is equal to L will be true if and only if x approaches a from the left, that value of the limit will be equal to L, or the left hand side limit, the left hand limit is equal to L, will be equal to the right hand limit. Okay, so as x approaches a from the right, so that limit will be equal to L, which is the same as the left hand limit. This common value will be the limit. Okay, so it doesn't matter if you approach uh, a from the left or from the right. Okay, if it gives you a common value, then that's called the limit. So therefore, you have the following statements that are equivalent. So we say that the limit of fx equals to L as x approaches a is the same. That statement is the same as saying that f of x approaches L whether you approach a from the left or from the right. Okay, so these two statements are the same. So if the function approaches L as x approaches a number a, then we can say it that we can say it, an equivalent way of saying it is that f of x approaches L whether x approaches a from the left or x approaches a from the right. So those are equivalent statements. Or you could say that f of x is close to L whenever x is close to a. Okay, so when x is close to a, then f of x is close to L. So those are that statement is also the same as the two previous statements a while ago. Another statement that are equivalent, another set of statements that are equivalent are the following. So you can say that the distance between f of x and L is small whenever the distance between x and a is small. So where do we see that? So if you make the distance between x and a smaller, okay, this is the distance between x and a. If you make it smaller and smaller, okay, then you make this distance between f of x and L smaller and smaller. So in this case, if I make x very, very small, I mean the distance between x and a very, very small, so this is my new x over here, I make it very small, then the distance of this new f of x, okay, call it f of x1, this is x1 over here, I can make this distance between f of x and L smaller. Okay, so whenever I make the distance between x and a smaller, I can make the distance between f of x and L smaller. Okay, so that's the first statement here. The distance between f of x and L is small whenever the distance between x and a is small. Okay, another um, more technical rendering of that statement is that given a positive number epsilon, no matter how small, so this is an epsilon, okay, so this is the distance f of x minus L, okay, f of x minus L over here, and this is the distance between this is the distance epsilon. Okay, so you have L here, you have if you add epsilon, then this is the new value. So this distance is actually epsilon. And this is the same as this distance where you net out epsilon. So this distance over here is epsilon. This distance is negative epsilon. Okay, so the absolute value is epsilon. Okay, so you can make the distance between f of x minus L, this distance smaller than epsilon. So in this case, this distance is smaller than this distance. Okay, so you can make it smaller than epsilon by choosing a small number delta, such that the distance between delta and the distance between x and a is smaller than delta. Okay, so in this case, this is delta, this distance between uh, x and a, for example, is delta. So it's saying you can always choose a delta, okay, where this delta is x minus a, this distance between x and a, okay? So if it's smaller than delta, you can always find, you can always make the distance between f of x and L smaller than epsilon. Okay, so that's quite a mental exercise. So it's just saying that you can choose a very small number delta whenever you can find an epsilon, and such that you can make the distance between f of x and L smaller than the chosen epsilon that you have. Okay, so epsilon is any number, and then this statement says you can always choose a delta wherein you can make the distance between f of x and L very small. Okay, great. Okay, so this is the formal definition of the limit. So we say that L is the limit of f of x as x approaches a, if and only if, when you choose a number, a positive number epsilon, okay, it's an arbitrary number, so it doesn't matter how small epsilon is, you can always choose a delta, a positive number delta, such that when the distance between x and a is less than delta, you can make the distance between f of x and L smaller than epsilon. Okay, so choose any epsilon. There is always that delta, which is the distance between x minus a, where the distance between f of x and L is less than epsilon. Okay, so that's a formal definition of a limit. So here are some theorems in limits. We'll not prove them. Theorems are meant to be proven, but we'll not prove them here. So the first theorem says that the limit of a constant, okay, if x approaches a, the limit of a constant is still that constant c. Okay, so for example, the limit of 7 as x approaches 5 is still 7. Okay, so the limit of x, just the variable x, okay, so it's it's this function, okay. The function is a variable of itself, so it's kind of like this one, okay. F of x is equal to x, so when x equals to 1, x equals to 1, f of x, so this is f of x, this is x, okay. So when x equals to 1, then f of x equals to 1, okay. So if f of x equals to 2, the value of f of x is equal to 2, okay, and so on and so forth. Okay, so if you have this function, if x approaches a from, so for example, this is a, okay. So if x approaches a, so whether from the left or from the right, the value of the function always approaches a, okay. Okay, so if x approaches a, the value of the function approaches a. Okay, so this is what this theorem says. So for example, the limit of x, okay, as x approaches 3 is equal to 3. Okay, so that's just what this theorem says. And so if you're getting the product of two functions, okay, so in this case f of x and g of x, if you get that product and you let the limit, uh, you let x approach a, okay, and the limit of that product, okay, is the same as getting the limit of f of x first as x approaches a, and then you multiply it by the limit of g as x approaches a. Okay, so you can do the limit of the function f first and then multiply it by the limit of the function g. Okay, so this is a corollary. So if one of the function is a constant function, okay, so for example f of x, I mean g of x is equal to c, then this is the same as the limit of g of x, or the limit of c as x approaches a. In this case, from the theorem a slide ago, this is equal to the constant, so this is c limit of f of x as x approaches a. Okay, so this one is a constant function, so the limit of that is constant. Okay, so if you have a square, for example, x squared, this is a function, then it's the same as the limit of x times x. So you can have the limit of x approaches a for x, okay, times the limit of x approaches a for this other x. Okay. Now you know from the previous slide that this limit is just equal to a, and this limit is just equal to a. So therefore, it's a times a squared. Good. Okay. So you have this function. Okay. And then as you let x approaches a, then a approaches, this is just a corollary of this one. So if you multiply x n times, right, so this is equivalent of saying limit of x approaches a, x times x times x times x, and this is you multiply x n times. Okay, so this is equivalent to this one. Then a corollary of this line over here says this is just a times a times a n times. Okay, so this is a raised to the n. Okay, and combining everything. Okay, so if you have this function with a constant here and x raised to n, that limit as x approaches a is just c, the constant c times a raised to the n. So that's the theorem. So if you have a sum or difference of two functions, f of x and g of x, then if you get the limit of that sum or difference, it's the same as just getting the limit of f of x first, and then add or subtract the limit of g of x as x approaches a. Okay, so if we have, for example, this function over here, it's 3x squared plus x cubed. So this is the same. This can be thought of as your f of x, 3x squared. This is your g of x, x cubed. Okay, so the theorem says that you can do this. You just get the limit of 3x squared first as x approaches 2, and then the limit of x cubed as x approaches 2. Okay, so as x approaches 2, then this limit approaches 4 times 3. This is 12. And this limit over here approaches 2 raised to 3. So this is 8. So this is equal to 20. Okay. So the limit of this function as x approaches 2 is 20. Okay. And so this other example, you can think of it, this one as your f of x, and your g of x is a constant. Okay. Which is equal to -1. So, or 1. So what you can do, according to this theorem, is you can get the limit of f of x first, this 5x squared, as x approaches 2, and then you can subtract the limit of the constant 1 as x approaches 2. In this case, as x approaches 2, this limit over here approaches 5 times 2 squared, which is 4 times 5, 20. And since this is a constant, as x approaches 2, then this limit is the constant 1. So 20 minus 1 is equal to 19. Okay, so that's just an application of this theorem. So if you have two functions, f of x of g of x, and you let f of x be divided by g of x, and then you take the limit as x approaches a, this theorem says that what you can do is take the limit of f of x as x approaches a, and then divide it by the limit of g of x as x approaches a. Now there's a caveat. This denominator should not be equal to 0, otherwise this limit will not exist. Okay, so as an example, you have this as your f of x, 2x plus 1, and this as your g of x, x cubed plus 4x plus 2. Okay, so what does the theorem say? The theorem says that this limit can be obtained by taking the limit of the numerator as x approaches a. So the limit of 2x plus 1 as x approaches a, then you divide that by the limit of the denominator as x approaches a. Okay, So, well, in this case, a is equal to 1. So as x approaches 1, okay, sorry about that. So as you do that, it's this limit approaches 2 times 1 plus 1. This is 2 plus 1 is equal to 3. Okay, and this limit in the denominator is approaches 1 cube plus 4 times 1 plus 2. So 1 plus 4, 5 plus 2, 7. Okay, so it's 3 over 7. Okay, so whenever you have f of x over g of x and you take that limit, it's the same as taking the limit of the numerator first, then divide it by the limit of the denominator, provided that that limit, the limit of the denominator, is not equal to 0. Now, as you may have noticed that whenever you have a polynomial, okay, that limit of the polynomial as x approaches a is taking that polynomial and substituting a for x. Okay, so for example, you have this polynomial over here, 4x to the fourth minus 3x squared plus 5x. Okay, and you're getting the limit as x approaches 1. So a in this case is 1. Okay, so what does this theorem say? You can just substitute your a 1 in this polynomial, and that's the limit. So in this case, you have 1 substituting for all of the x's here. Okay, so it's 4 times 1 raised to the fourth minus 3 times 1 squared plus 5 times 1. So this is 4 minus 3 plus 5. This is 1 plus 5 is equal to 6. Okay, so that's what this theorem says. If your function is polynomial, that limit is just simply substituting the limit a, the value a to the polynomial. So whenever you have, for example, you have two functions, f of x and g of x, both of them are polynomials. Okay, and then you divide f of x by g of x and get that limit. Now this theorem says that this is equal for this is equal to this process where you substitute a for x for f and then divide it by substituting a for x in g. Okay, so you divide f of a and g of a. Now, provided again that g of a should not be equal to 0, otherwise this will not exist. Okay, so for example, you have this polynomial over here. This is your f of x, 3x squared minus 5x plus 2. And this is your g of x over here. This is another function, x cubed plus x squared minus 8. Okay, so you want to get that limit as x approaches 3. Now what this theorem says is that you can substitute the value, this a over here, in this case 3, to the function above for all the x's above. So 3 times 3 squared minus 5 times 3 plus 2. Okay, then you divide it by the function below where you substitute all the x with 3. Okay, so this is 3 cubed plus 3 squared minus 8. So yeah, this is 9, 27 minus 15, 12 plus 2 is 14. This is 9 plus 27 plus 9. This is 36 minus 8, 28. So it's 14 over 28, or 1 half. Suppose now that you have a function f of x, okay, f of x over here, and you raise it to a number n, okay, and then you want to take that limit as x approaches a. This theorem says what you can do is to take the limit of f of x first as x approaches a, then you raise it to n, to that number n, which is a positive integer. So for example, you have this f of x, x3 minus 6. Okay, so that's the function. And then you raise it by 5, raise it to 5, and you get that limit as x approaches 2. What this theorem says is that first, what you can do first is just take the limit of f of x as x approaches 2. So what's that limit? Well, as x approaches 2, this approaches 2 cube, okay, 2 cube minus 6, this approaches 8 minus 6, 2, okay? So this is 2, okay? Then you raise it by whatever this positive integer is. In this case, it's 5. So you raise 2 by 5, so it's 2 times 2 times 2 times 2 times 2, 2, 4, 8, 16, 32. Okay, so 2 to the 5th, 2 to the 5th is equal to 32. Okay, so that this is what this theorem is saying. Okay, so here's another theorem on the limit of a power. So for example, you have this function f of x, okay, and you want to raise it to 1 over n. Okay, so what's what raising it to 1 over n? So raising it to 1 over n, for example, n equals to 2 is just getting the square root. Okay, and in this case, n should be even, so you can only admit 1/2, 1/4, 1/8, and so on and so forth. Okay, so if you have that function and you want to take the root, okay, so 1 over n, you raise it to 1 over n and you get the limit as x approaches a, then that is equivalent to getting the limit of f of x first as x approaches a and then raising it to 1 over n. Now notice that this one, this is the limitation, this limit should be positive as x approaches a. Because if this limit is negative, then for example, this limit is negative 1, okay? So you're getting 1/2, for example. Is this equal to you're raising it to 1/2, so this is equal to square root of negative 1, which is not a real number. Okay, so this is the condition. This limit should be positive as x approaches x approaches a, and moreover, this is another condition that n should be positive and it should be even. So for example, you have this function x squared minus 3x plus 5, and you're getting the square root. So this is same as limit of x as limit as x approaches 1 of x squared minus 3x plus 5. This is the function. Okay, this is of f of x, and then you're raising it to 1 over 2 to 1/2. So this is the same as this one. Okay, it's just taking the square root. So what does this theorem say? The theorem says that you can take the limit of f of x first, okay, and let x approach 1. So since this is a polynomial, this is equal to substituting 1 for each of the x's here. So this is 1 squared minus 3x plus 5, 3 times 1 plus 5. This is equal to, what's that, 5 minus 3, that's 2 plus 1 is equal to 3. Okay, and then once you get that limit, you raise it to 1 over n. In this case, you're raising it to 1/2. This is equal to square root of 3. That's why you have a square root of 3 over here. Okay, so this is an example of how you apply this theorem. Now let's go to some special cases. Now suppose you have this function over here, uh, x squared minus 1 divided by x minus 1. Okay, so we had a theorem earlier that, um, well, you can take this limit of f of x, and then if you have another function, uh, you can have this limit, take this limit, okay, and that will give you the limit of this function. But in this case, an important caveat is that the denominator should not be equal to 0. So this one, you cannot apply this theorem that what we had a while ago. Okay. However, when x is not equal to 1, what you can do is that you can uh, expand this one. X squared minus 1 is just the same as x minus 1 times x plus 1. Okay, and notice that you can cancel therefore this denominator with this part of the numerator, and you're left with x plus 1. So therefore, when x is not equal to 1, this limit as x approaches 1 is equal to 2. So graphically, this is what it looks like. Okay, if we exclude 1, x equals to 1. Okay, if we exclude this, so there's a hole here. Uh, Whenever you approach x from um, 1 from the left or from the right, okay, you will approach f of x equals to 2. Okay, so as you go closer and closer to 1 from the left, the value of f of x goes closer and closer to 2. If you um, approach 1 from the right, the value of f of x goes closer and closer to 2. Okay, so this one. Okay. As you move from x closer and closer to 1 from the right, it approaches 2. If you move, if x moves closer and closer to 1 from the left, then this value also approaches 2. Okay? So when if x is not equal to 1, then this limit approaches 2. So here's another function. Okay, suppose you have this function 1 divided by x minus 1. Now let us approach 1 from the right. Okay, so from values bigger than 1, say x equals to 1.1, then 1.05, then 1.01. Okay, so it becomes closer and closer to 1. Okay, so from values bigger than 1, let's move closer and closer to 1. Now you notice, for example, this is a positive number. For example, 1.1 minus 1 is zero point 0.1. Okay, then if x is 1.1, then this is 1 divided by 1.1.1. Okay, and if x is equal to 1.05, then this function over here is 1.05 minus 1 is 0.05. 1 divided by 0.05. And then this one is 1 divided by zero point 0.01. Now you notice that as you go from here to here, the value explodes. Okay, so goes, it increases without bound. Okay, so the limit is therefore positive infinity. Okay, so it increases without bound. This limit does not exist. Okay. On the other hand, if you approach this function, x from the left for this function, so for example 0.9, then 0.95, and 0.99, for example, so you're going from values lower than 1, and then you're approaching 1. Okay, so if that's the case, then this function over here is 1 divided by zero point 0.9 minus 1 is point negative zero point 0.1. Okay, so this is a negative number. The whole thing is negative. Then this is, if x is equal to 0.95, then this is 1 divided by 0.95 minus 1.05. This is negative. This is a bigger number compared to this one. Now if we go further, then this is 1 divided by zero point 0.01, negative. Okay, if we minus, if we subtract 1 from 0.99, we have negative zero point 0.01. So this value is a bigger negative number than this one and this one. So you notice as you get closer and closer to 1 from the left, then you'll have a bigger and bigger negative number. So therefore, the limit is negative infinity. So it decreases without bound as x approaches 1 from the left. So therefore, this limit does not exist. So if you graph that function graphically, this is what happens. So if you approach 1 from the left, okay, so this is 1. If you approach 1 from the left, okay, 1 closer and closer to 1, you see that this function increases to negative infinity without bound. Okay, if you approach 1 from the right, okay, then this function increases and increases without bound. Okay? So this limit as x approaches 1 does not exist. So in those two previous examples, we see that in the first case, this function f of x has a break at x equals to 1 because it's undefined at x equals to 1. Okay? In the second case, in the second case, we have this function. Uh, this function f of x has a break at 1, and it's undefined at 1, x equals to 1, because you see that this function increases without bound, and here it also increases without bound. This one decreases without bound. Okay, so th- those two functions have breaks at this point. Okay, at x equals to 1. Now, if you recall our example earlier, um, when we had the definition of left hand limits and right hand limits, we have this function from a while ago. You see that this function is defined at x equals to 0 because you can, it's defined via this part of the function. Okay. However, uh, when you say approach 0 from the left, you approaches this approaches 1. Okay. But then again, as you go to x equals to 0, boom, okay, it jumps to x equals to f of x equals to negative 1. Okay, so this function has a break because when you were in this side, you were approaching 1, f of x equals to 1. Suddenly, as you go to 0, boom, it's now f of x equals to negative 1. Okay, so that function has a break. So therefore, we have the intuition of what a continuous function is, or or a discontinuous function is. Okay, so whenever a function has a break, they are discontinuous at those breaks. Okay, so a continuous function intuitively is a function that has no such breaks. Okay, so the layman's definition of a continuous function is that you can draw the graph of that function without lifting your pencil. Okay, so this is a continuous function. Okay, but this one is not a continuous function. Okay, because I lifted my pencil here. Okay, so more formally, we have a function f of a one variable x. Okay, so it's just a function of a variable x. This function is continuous at x equals to a certain value a, if and only if, okay, f is defined at x equals to a. Okay, so in the example a while ago, there was at x equals to 1, the function was not defined. Okay, so it must be defined at x equals to that uh, value of that value a. Or alternatively, you see that the limit of the function as you approach from the left should be equal to the limit of the function as you approach to the right, and that common number should be the limit. Okay, should be equal to the limit of the function. So the second example that we had, where you had graph where one is in, decreasing unboundedly at x equals to 1, and one is increasing boundedly as x approaches to 1 from the right, you see that the limit does not exist and the limit is not the same, so therefore it's violating 1 and 2. Okay, and the third one is that that limit as x approaches a should be equal to the value of the function when you substitute a over here. Okay, so an example would be this function f of x equals to x. Okay, so when you approach a value a, okay, when you approach a value a, then that limit should be equal to f of a. Okay, So when this exists, this function is continuous. Okay. So here are some theorems. We'll not dwell on this, but if you have two functions f and g, which are functions of one variable x, then they're continuous at x equals to a point A, and each of them are continuous at x equals to A. Then their sum, f plus g, their product, f of g, and when you divide f divided by g, that resulting, okay, provided that g is not equal to 0, g of a is not equal to 0, these three are also continuous at x equals to a. Okay? So here we have a composite function. So h of x is defined by uh, uh, putting in f of x to the function g. So h of x is a composite function. And we have that f is continuous at x equals to a, which means that f of a, this limit as x, uh, this limit as x approaches a of f of x is equal to f of a. Okay, and g is continuous at f of a. Okay, if you put in f of a into g, then it's continuous. Then therefore h is also continuous at x equals to a. Okay, so remember that f is continuous whenever you have, um, let's go back a few slides. So whenever this one happens, the limit of f of x as x approaches a equals to f of a. So if that's true, then in this composite function, f of a exists. Okay, f of a exists, and if f of a exists, and you put in f of a here at g, and g is also continuous at f of a, then this composite function h of x is also continuous at x equals to a.